You can start.
I'm Shanna, this is Justice and Sam, and we're going to talk about different forms of internal corrosion. Got that? We are going to talk about velocity-related corrosion, which includes erosion, corrosion, impingement, and cavitation. We'll also talk about microbiologically influenced corrosion, or MIC. This includes acid-producing bacteria, which is APB, sulfate-reducing bacteria, SRB, and then fungi, algae, and protozoa. And we'll also talk about other problems associated with non-corrosive species, which include fouling and scaling. First, we're going to do velocity-related corrosion, erosion, cavitation, and impingement. Erosion is the progressive loss of materials from a solid surface up the pipe. It's where you get mechanical interaction between the surface and a fluid. Can be multi-component fluid or solid particles carried within a fluid. In this picture, the blue arrow is pointing to where the pipe has not had any erosion. The red arrow is pointing to where there has been some erosion of the pipe. And this is also showing erosion. The top one has not had erosion, where the bottom has had that film taken away. And this figure also shows where the erosion is going to occur the most. Commonly occurs within the bend of a pipeline rather than at the straight. When it's straight, you have less chance of the erosion happening. Where when you have lots of curves, you're going to get more erosion. It's most common in copper and in steel pipelines. It occurs due to quick flowing liquids, and it wears away the protective coating from the pipes, and it leads into erosion corrosion. Mitigation, you need to do proper dimensioning, selection of suitable materials, use of inhibitors or other erosion reducing measures. You also, material selection, and monitoring and inspection of flow control. A lot of ways to test it would be is to use your pipe wall gauges and ultrasonics.
Alright, so we talked about erosion, now we can talk about erosion corrosion. Since erosion corrosion happens only after erosion takes place, and it's an acceleration in the rate of corrosion attack on a material due to relative motion of a corrosive fluid on a metal surface. Alright, so first it starts off as just erosion, and so the liquid is just wearing away the film on the inside of the pipe. And so whenever the film is taken away, the metal reacts with the liquid. Since it wasn't in contact, now it's in contact. It can start off with a chemical reaction or whatever happens to it. And the turbulence accelerates erosion corrosion. That's the liquids are moving all around, throwing around all types of particles, and it's slamming into the wall and starting like cavitation and breaking off the metal pieces. And it's common in copper and steel piping, mainly because the what would you call that? The coating that's on the inside of the pipe, there's a film that copper and steel produce gets worn away a little bit too easy because it's too thin. Alright, erosion corrosion environments happens in places that have a constant or fast flow of liquid on the inner lining of the pipe, and in constricted areas because everything will want to be thrown into the wall of the piping, so it'll corrode more. And sharp turns, just because it changes the momentum of the liquid, which has solid particles or gases in it, and it goes straight into the pipe wall, and it has to keep flowing, and it causes more turbulence, which right here shows you how the liquid it keeps on throwing up all the water and the liquid particles, and it just keeps getting worse and worse, and that leads to erosion corrosion. And on the inside of this, it's a sharp turn, so you're probably going to have more erosion corrosion. This right here, it shows you the way it's going, and it doesn't really happen until it hits that sharp turn. So that's really the main point at where erosion corrosion happens the most. So, to mitigate erosion corrosion, you want to reduce the turbulence of the fluid. You don't want to have the fluid going too fast to where it's pretty much always going to mess up your inner lining of your pipe. And control the flow of the liquid, you can monitor that. Just make sure you're not at speeds at which it'll rapidly degrade your material. You want to always replace the sharp angles with gentler ones, just because that's the main reason erosion corrosion happens. And you can remove the solid particles by filtering, because the solid particles are just contributing to the factor that erosion corrosion produces. And select the proper materials. You want a material that has a protective film that's thick enough to withstand all the objects getting thrown at it.
And next we have cavitation corrosion. All it is a formation and rapid collapse of cavities or bubbles within a liquid, which often result in damaged materials, solid liquid interface, and conditions to severe turbulent flow. So wherever water is flowing fast, it's going to tear down metal. It's a given. Environments are pump impellers and engine pistons. Anytime liquid moving, metal's moving, it's going to clear it away and cause cavitation. Materials susceptible to cavitation is brass, copper, nickel, and right here you can see that as a impeller turns, where the water hits it, it's going to have cavitation. Testing methods of ultrasonics were used to test for cavitation. Cavitation tests were made under free corrosion conditions and function exposure time to natural seawater. So mitigation for it, cavitation can be mitigated by using CP or inhibitors. I've also used them to prevent it. Impingement corrosion is almost repetitive. Impingement follows cavitation. Wherever you find cavitation, there's going to be impingement to follow. Impingement corrosion is a form of erosion corrosion generally associated with local impingement of high velocity flowing fluids against the solid surface. Environments, also cavitation, impingement, going to find on pump impellers, engine pistons. Materials that are susceptible to it are also brass, copper, and nickel. Testing methods, I researched and I could really couldn't find very much, but there was one that consists of open cage spindle containing flat coupons rotated at a set speed of rotation to generate high local shear stresses leading the edge of the coupons. Inhibitors are also used to mitigate it.
Mid corrosion is corrosion assuming loss of metal caused by biological organisms. Next one. It's a serious corrosion that impacts the operating integrity and reliability of assets in the industry, and it can lead to some pretty severe corrosion. This is a picture of some of the corrosions, highly localized corrosion shown in the figure is typical of that resulting from microbial action. Mechanisms that take place in the presence of microbial consortia in many physiological types of bacteria, including metal oxidizing bacteria, sulfate producing bacteria, acid producing bacteria, and then metal producing bacteria, which they all interact in complex ways and cause within the biofilms, sorry guys, they form biofilms, and underneath those biofilms is where the corrosion is going to take place. And then this picture is actually out of our corrosion Bible that shows how exactly it goes. You have your anaerobic bacteria. Organic matter can be anything from dirt, any loose particles, and then you have your aerobic bacteria, and they form this biofilm, and it's kind of like I've seen, if you've worked with any pipes, taken them apart, a lot of them will have a film built up. Underneath this film is where localized pitting and corrosion is going to take place. Forms of Corrosion is acid-producing bacteria, sulfate-reducing bacteria, and then fungi, algae, and protozoa. Those ones we're going to focus on today. Sulfate-reducing bacteria. It's a bacteria that can obtain energy by oxidizing organic compounds or molecular hydrogen by reducing sulfate to hydrogen sulfide. And most sulfate-reducing bacteria can also reduce other oxidized inorganic sulfur compounds, such as sulfite, sulfate, and elemental sulfur. Here's a picture of a pipe that they've taken apart because customers have been complaining about some offensive odors. And that is one of the ways that you can tell if there's sulfur with SRB in the pipes. There'll be an odor, and so that's what they found when they took it apart. Mechanisms of it are correlated with groundwater sulfate concentration. That'll grow in soil, freshwater, saltwater, under anaerobic conditions. And factors of it are temperature, nutrient availability. There's lots of nutrients that the sulfate-reducing bacteria like. You're going to find a lot of it. Sulfide inhibition and adhesion to cells to metal surfaces. Mild steel and carbon steel are the most widely used materials, and also most susceptible to forming the patchy biofilms on the surface. The SRB forms an unstable and continuously growing layer of inorganic products, causing more corrosion. This form of corrosion follows the, I'm trying to say the Arrhenius equation, this being the cathodic step right here, and your anionic step here. All right, and then these pictures are we're only in the are from only 10 days in the ground with the sulfite or SRB bacteria. It just shows you how quickly it can attack the material. It can normally will be pretty. Anyways, it's very localized. Methods for testing: we do liquid sample, PR probes, coupons. Coupons are just quite a bit for it. The mitigation of the sulfate-reducing bacteria. You can do organic biocides, and there's a list of them. Now, talking with, I have a friend who does this for a living, and talking with him, he said it's very hard for them to be able to mitigate it because there's bacteria everywhere, and no matter how quickly you do it, or with some of these biocides, they won't work all the time. So you have to understand that no matter how quickly you mitigate it, there will still be some form of it. So it's never fully gone. And then also, on the next slide, biostats, which is a lubricating oil that contains selected additives, which ensures efficient oxidation stability, good anti-corrosion and anti-wear properties, along with low aquatic toxicity. And this is what he said they use more of, along with bleach. But I could not find anywhere that could give you a good reference for just bleach. So there you go with that. And then also you have acid-producing bacteria. It's recognized as a possible major cause of corrosion, mainly because its fermentative activities will cause the pH to drop drastically into the acid range. And then under these conditions, an acid-driven form of corrosion could occur where the metals begin to dissolve and concrete structures lose integrity along with pipes. Acid-producing bacteria will cause localized form of corrosion in the form of pitting beneath biofilm. And so here's just a few pictures of this pipe. It's capable of producing organic and inorganic acids. Like I said before, significantly drops that pH into that acid range. And acid-driven form of corrosion occurs. It causes metals to dissolve and concrete structures to lose integrity. And acidic metabolic byproducts are used under very productive oxygen-free environments. And acidic metabolic byproducts are produced under very productive oxygen-free environments. That includes SRB, which is found in a nutrient-rich oxygen-free environment. The testing is very similar to the SRB. Testing liquid samples, ABB, BART tests, and then ER probes as well. And the mitigation for us is the same. Organic biocides and inorganic biostats, which is the lubricating oil. And these are pictures of some of the localized corrosion pits formed in the pipe wall. And these were formed underneath the biofilm layer. On-off for mitigation, discrete deposits are even harder than biofilms to penetrate biocides and chemical treatments. They reduce cathodic protection and efficacy, which makes eliminating native bacteria and protecting the metal beneath the deposits very challenging. And it's an ongoing process.
Scaling, it's a formation at high temperatures of thick corrosion product layers on the metal surface. The deposit of insoluble consistence of metal surface. It's hard water hitting the metal. Scaling there they are. Boilers, coils, sprinklers, and cooling systems, wherever hard water is used. There we go. Here's the simple scaling. Cast iron, carbon steel, and copper. The mechanism, scaling involves adjusting the inch-string scale of patterns out of, that's the mechanism of scaling right here. Methods of testing, measuring the conductivity of the solution coming out of the piping system. Mitigation for scaling. The best one to do is control the pH. That will stop scaling pretty much. The addition of scale inhibitors and the removal of scaling species.
Alright, fouling is the settlement and growth of undesired materials on a solid surface, and it always reduces the efficiency of a part or a system or a piping system. It occurs in areas where settlement is encouraged by design. By example, heat exchangers that on the bottom, they have lots of heat and cold, so there's a lot of materials that like to settle down on the bottom, and they just deposit on the bottom, and it kind of messes up how the heat exchanger works. Pipes that carry water as a coolant in cooling towers, most of the time they have more particles and solid particles that end up being deposited on the bottom of the pipes. And electrical heating elements was the heat exchanger. And this shows the fouling occurring in here. That's a lot of deposits being made in there. And yeah, it was cut in half. The water, whatever was going through there, wasn't moving through very well, so it kind of hurt the piping system. It may be caused by the operating environment or by an equipment process. See, right there is the bottom of a heat exchanger. All the materials coming in with the heat and the cooling, it mixes and it ultimately settles on the bottom and hurts the efficiency of the heat exchanger. Biological deposits, such as if there's organisms, they could be taking dumps and leaving it at the bottom of the pipe, and it'll start eating away or reduce how it was working. And the decomposition of those products as well. the way to monitor and mitigate it is visual inspections, or if you have something that can tell how fast something is moving through the pipe, you'd kind of know if there was not much fouling or not, if it's running smoothly, or it just randomly starts getting slower or less fluid flowing through at the same amount of time. You want to prevent the fouling material from entering the system in the first place if you could, but in some instances you really can't because that's just part of the process that it has to go through. And you can use chemical treatments to control air in the cooling towers, which would help, I guess, the particles in there would be maybe eaten up or something by the chemicals. Also, fungi, algae, and protozoa is the mid corrosion. They're all microorganisms that exist as unicellular, multicellular, and cell clusters, and it's corrosion resulting from the presence of microorganisms. Alright, well, fungi, produce spores that are resistant to temperature and diverse conditions. Like, a lot of fungi can resist boiling water, being in an acidic environment or alcohol environments. So they're very diverse and they're kind of hard to kill. And it occurs in areas where it contain nutrients for spores and to grow and reproduce. Algae are photosynthetic organisms with low requirements of light, water, and air. Photosynthetic production of oxygen develops corrosive species such as organic acid. And it occurs in areas with nutrients to feed on. So algae likes to feed on stuff, carbon dioxide. It's always sitting on the metal. So like you have algae sitting on your boat that's sitting in the water. So it has a lot of stuff to feed on, so it's just going to be able to thrive and live there pretty much forever. Protozoa, they're single-cell organisms that often have complex and highly ordered structure, and they feed on other organisms such as bacteria, protozoa, and fungi. So if you have a bacteria and fungi problem, you might have a protozoa problem too because they like to feed on all of them. They can all be mitigated